Hi everyone. In this video we're going to get some background information so that we can start talking about chemical reactions. But first let's talk about how chemists can count up these atoms and molecules and mix them together to do reactions. So chemists count these atoms by weighing them. And it turns out that there's a convenient number to weigh, and that's Avogadro's number. It's a 6 followed by 23 zeros. And it's convenient because if you have this many number of atoms, those atoms will weigh the atomic weight in grams. So let's do an example. 6 times 10 to the 23rd atoms of, you pick the element, I don't know, let's try carbon. Well, go to the periodic table, look up the atomic weight, it's the bottom number, and for carbon it's 12.011. And if you have Avogadro's number of atoms of carbon, they'll weigh 12.011 grams. So what we can do in the laboratory is start dumping atoms onto the balance. And let's say if you're weighing out some sulfur, if you stop at 32.066 grams, you will have Avogadro's number of sulfur. What about molecules? Well, that's easy enough. Just add up all the atomic masses for the atoms that show up in the molecule. So, if you have 6 times 10 to the 23rd molecules of water, they will weigh, well, the chemical formula is H2O, so we have two H's and an oxygen. On the periodic table, Avogadro's number weigh 1.0079 grams. Well, let's just round that off to 1 gram. Oxygen, well, Avogadro's number weigh 15.9994 grams. Let's round that off to 16. So, Avogadro's number of hydrogen weighs 1 gram each. Oxygen, Avogadro's number weighs 16 grams. Add those up. 1 plus 1 plus 16 equals 18 grams. So if you have Avogadro's number, 6 times 10 to the 23rd molecules of water, they will weigh 18 grams. You can do it for bigger molecules too. So blood sugar, which is also called glucose, well, there's 6 carbon atoms in one molecule, 12 hydrogen atoms, and 6 oxygen atoms. Let's write ox so it doesn't look like a 0. And each carbon, I think we said it weighs 12 grams. Yeah, let's round it off to 12. The atomic mass or atomic weight of carbon is 12. Hydrogen, well, we just said that equals 1 gram each, Avogadro's number. And oxygen, 16 grams. So let's see, 6 times 12 is 72. 12 times 1 is 12. 6 times 16, let's see, 6 times 6, 36, carry 3, 96. And now add them up. 2 plus 2 is 6 is 10, carry 1, 8, 9, and 9 is 18. There we go. Avogadro's number of glucose will weigh 180 grams. Well, instead of saying Avogadro's number all the time, or 6 times 10 to the 23rd, chemists just say the word mole. I think mole is just short for molecule. So molecules, mass, molar mass. It's very similar to bakers just saying dozen all the time instead of saying 12. So chemists say mole instead of 6 times 10 to the 23rd, Avogadro's number. So here, let's start getting used to that idea of replacing the word mole every time you want to say 6 times 10 to the 23rd. Well, the bakers, they do it just fine. If you have 2 dozen donuts, well, every dozen is 12. And if you have 2 of those 12s, 2 of those dozens, that's 24. If you have half a dozen, well, that's half of 12. That's 6. Same thing for moles. A mole is 6 times 10 to the 23rd. If you have 2 moles, you have 2 Avogadro's number. 2 times 6 times 10 to the 23rd is 1.2 times 10 to the 24th. If you have half a mole, the mole is 6 times 10 to the 23rd. Well, half of that would be 1/2 of 6, which is 3. 3 times 10 to the 23rd. Here's a few more practice problems. How many grams does 2 moles of hydrogen atoms weigh? Well, a mole is Avogadro's number, and 1 Avogadro's number of hydrogen atoms weigh 1 gram, right? Yep, Avogadro's number, we'll just round it off to 1 gram. So if you have 2 Avogadro's number of hydrogen, you have 2 times 1 gram, 2 grams. How about if you have half a mole? Well, you're going to have half of 1 gram. That's going to be half a gram, or in decimal, 0.5 grams. Well, how about half a mole of water? How much does that weigh? Well, 1 mole of water, 1 Avogadro's number of water, 6 times 10 to the 23rd, water molecules, we said that equals 18 grams. Yeah, Avogadro's number of water molecules equals 18 grams. So if you only have half a mole, half of that quantity, well, half of 18 is 9. Yep, half a mole of water will weigh 9 grams. Half a mole of glucose, well, we said Avogadro's number of glucose molecules is 180 grams. So if you have half a mole, half of Avogadro's number, that's 90. You know what? When we said Avogadro's number's worth of glucose molecules weigh 180 grams, we could also say 180 grams per mole of glucose. So the units of molar mass are grams per mole. And then finally, we can use dimensional analysis or unit conversion to do these same calculations. So let's look at this sample question. How many moles of helium are in 12 grams of helium? So remember dimensional analysis? We begin by asking ourselves the question, okay, what do we want? We want moles of helium. So write those units over here on the right. We want moles of helium. Leave a space for the answer, equal sign and a line. Then ask yourself a second question. What number are we given? What information? We're given the number 12. And the units for the 12 are grams of helium. So write that on the top left. So we're told take 12 grams of helium and change them into units of moles of helium. So that means we need to find a conversion factor. Step 3. We need a conversion factor to cancel out this grams of helium, and change them into moles of helium. So we need some conversion factor with grams of moles in it. Yeah, that's molar mass. Molar mass. So go to the back of the periodic table and get that conversion factor. If you have 1 mole, if you have Avogadro's number of helium, well, helium has an atomic mass of 4.0026. Avogadro's number of helium will weigh about 4 grams. 1 mole of helium, 1 Avogadro's number of helium, weighs about 4 grams. So now do the math. 12 times 1 is 12. Divide by 4. That's 3. The answer is 3 moles of helium will weigh 12 grams of helium. Okay, now let's talk about soaps and detergents. Okay, soap and detergents are useful for cleaning your clothes, cleaning your hands, right? And usually what happens is you have oil and dirt, something greasy on your clothes or on your hands, and water won't remove it. And that's because oil and water don't mix. Oil contains nonpolar molecules, but water's polar. So, in order to get the oil and grease off your hands, off your clothes, we use soaps and detergents. Soaps and detergents are molecules that contain both nonpolar and polar parts of their molecules. So, the majority of this simple soap molecule, this is a soap molecule, has a nonpolar feature. There's a bunch of carbon-carbon bonds, right? The same 2 elements attached to themselves. They share equally, and we have a nonpolar covalent bond. The carbon-hydrogen bonds are defined to be nonpolar covalent. So yeah, every bond in this part of the molecule is a nonpolar covalent bond. And they're just like the molecules found in oils. They're going to be nonpolar. This part of the molecule is also nonpolar. But at the end, we have oxygen here doing something interesting. It's sharing electrons between carbon and oxygen, right? Those are 2 nonmetals, but they're different. They have different electronegativities. That's a polar covalent bond. And there's a bond between oxygen and sodium. Sodium is a metal and oxygen's a nonmetal. And when a metal bonds to a nonmetal, they usually form an ionic bond. So oxygen's negatively charged and sodium is positive. And with the polar covalent bond, let's look at this double bond to oxygen. The oxygen is slightly negative, the carbon is slightly positive, as those electrons are not being shared fairly. They spend more time on oxygen, making it slightly negative. So the end result is this end of the molecule has a lot of charges. It's very polar, just like water's polar. So if we look at the soap molecule in this drawing, we can circle this long tail, this long chain, as the nonpolar part. We can circle the end part here as the polar part. And then if you dunk this in the water, well, they start associating with each other. The greasy tail avoids the water, and they start sticking to other soap molecules, and they get away from the water on the outside. And the polar head group here, the circle part, they're polar. They can associate with the water, and they stick to the water. And what you get is a structure called a micelle. Here's a different drawing with the same type of thing. It's more three-dimensional. You got the water here in blue and all these little circle groups, the polar groups. The ionic bonds and polar covalent bonds are sticking towards the water. Whereas the greasy tails, the nonpolar parts, are all clumped all together in the middle. And it looks like we got an oil droplet in the middle here. The nonpolar molecules are also sticking to the tails. And that's the feature that we need in order to understand soaps and detergents and how they clean surfaces. So here's a surface. Maybe it's your hands, maybe it's a countertop with a bunch of grease or dirt. And those molecules tend to be nonpolar molecules. And you rinse off the surfaces, rinse your hands. The water doesn't cut the grease. They're too different from each other. They don't dissolve in each other. But then you add a bunch of soap molecules. The circle groups are polar. They can associate with the water here. And the greasy tails, the nonpolar tails, they can stick to the greasy nonpolar dirt and grease molecules. And it starts lifting them up from the surface. And it starts packaging them together into a micelle. The greasy dirt molecules, they're going to be in the middle, associated with these tails. The polar head groups are going to be surrounding them. And this whole thing then can kind of float or mix in the water. And it can just rinse down the drain. And then you get a cleaner surface. Okay, let's introduce chemical reactions. One way to defining them is to think about taking a bunch of molecules, the reactant molecules, and shuffling the atoms. Breaking off the atoms from one molecule and sticking them onto a different molecule. And you make new molecules that way. Now, in a real system, these molecules have to collide in order to react. And they have to collide with enough force that they break the ionic or covalent bonds that hold the atoms in place, because we need to shuffle them. So you have to detach the atoms from one molecule and stick them on another molecule. And in order to break those atoms free, these molecules have to collide with enough force to break those bonds. Well, if they don't hit hard enough, the bonds won't break and you'll get no reaction. So how do you get more reactions to happen? Well, you need those molecules to hit with more force. They need to have more kinetic energy, more motion. And temperature is a measure of the average kinetic energy. So, if you increase the temperature, the molecules are moving faster. They have more kinetic energy, which means that they're going to collide more often and with more force. So, increasing the temperature increases the rate of reaction. Another way to speed up a reaction is by using a special molecule or special type of molecule called a catalyst. And these are molecules that speed up reactions without being used up. And that's pretty cool because after the reaction's all done, you can go and collect these catalysts and use them again. The catalysts that nature tends to use are called enzymes. They're special proteins. Proteins that speed up reactions without being used up. Okay, finally in this video, let's introduce chemical equations and how to balance them. Okay, chemical equations are kind of like recipes. What we're going to say is, hey, let's take a whole bunch of reactant molecules, and those molecules are going to break apart and reshuffle the atoms to make new molecules that we call products. And when you do a chemical reaction, you can't lose pieces. You can't lose some of those atoms along the way. And you certainly can't just magically create atoms. No, the same number of atoms that start out in your reactants have to end up in your products. Or in other words, that's the law of conservation of mass. Mass is neither created nor destroyed. So the number of atoms that go into the reaction has to equal the number of reactions leaving. Let's look at some examples. Here's an example of a chemical reaction. Hydrogen gas is explosive. And in order to burn, you need oxygen. And so mixing oxygen with hydrogen gas, and then you need to start with a spark, you get a big explosion, a lot of noise, a lot of light, but you also produce water. Okay, this recipe is not balanced. This chemical equation is not balanced because, well, we start with 2 hydrogens and we end with 2 hydrogens. That is balanced. But we start with 2 oxygens, and right now, we only have 1 oxygen. Well, where did that second oxygen go? Well, it has to be there. We have to balance this equation to show that the oxygens are not being destroyed along the way. That doesn't happen. No, they're just being reshuffled, right? So we're going to take a hydrogen molecule, two H's, and an oxygen molecule, or the Lewis dot structure for oxygen gas. And what we're going to do is break them apart and take an oxygen and 2 H's, link them together to make one water molecule, but hey, we have a leftover oxygen. Well, this recipe says you can only make water. So what we need to do is add a second hydrogen molecule so that we have a total of 4 H's to react with 2 O's, and we get out 2 water molecules. The second leftover oxygen then can react with these 2 H's. This breaks apart, and then the oxygen will combine with 2 H's to make the water molecule. Okay, so that's what we need to do. We need to balance the equation. That's one of the longer ways of doing it. Here, let's look at some shortcuts and some advice on how to balance equations. Step 1, don't change the subscripts. Right? If you change a subscript, that's going to change the recipe. So what I'm going to show you is wrong, so don't do this. But you can look at this and say, hey, there's 2 H's, 2 O's. I only have 2 H's here. I only have 1 O. So let's just put a second one there. That's wrong. What we've done is we've changed the recipe. H2O2 is not water. That's hydrogen peroxide. Okay, that's an oxidizer, sort of like bleach. So yes, you can do a reaction where you mix hydrogen gas, oxygen gas to make hydrogen peroxide. That's a different chemical reaction. So if you're trying to balance this reaction where you mix hydrogen and oxygen to make water, well, you can't change the subscripts. That's out of bounds. That's wrong. Okay, let's try it a different way. So instead, what you want to do is save the simplest molecule for last. So if you look at these molecules, these first 2 are pretty simple. They contain contain one type of element, just hydrogen or oxygen. This molecule is more complicated. It has 2 different elements present. So you can choose the hydrogen gas or oxygen gas to be your simplest molecule. Save it for last. I'm just going to randomly pick the hydrogen to be the simplest. So what that means is start by balancing the oxygens. So there's 2 over here and 1 over here. In order to get a second oxygen over here, you have to have it packaged as water. That's what the recipe says. You only make water. So all your oxygens have to be tied up with 2 H's to make a water molecule. Okay, so that's what we're going to do. We're not going to make 1 water molecule. We're going to make 2. So that together, there's 2 O's to balance these 2 O's. But if you change the number of water molecules, that changes the number of hydrogens. We now have 4 on this side. So we're going to need another hydrogen molecule over here, 2 more H's, so that together we have 4. So one way of writing the balance equation is writing it this way. But this is redundant, right? There's 2 molecules of H2. So a better way of writing it was with a big 2 in front. And there's 2 water molecules. So put a big 2 in front of that too. And then we should include the physical states. Hydrogen is a gas, oxygen is a gas. And then in this reaction, because it's so explosive and so hot, the water is going to come out as steam. So that's going to be a gas. But you could say that the water then later cools off and it's a liquid. Your choice. Let's do another one. Okay, here's the reaction for a gas stove or a gas furnace. Natural gas is mainly CH4, methane, and it burns in oxygen, and it turns out it produces carbon dioxide and water. So let's balance this equation. Well, is it already balanced? Let's check the number of elements on each side. There's 1 carbon on each side. There's 4 hydrogens, but oops, nope, hydrogen's not balanced. We start with 4 hydrogens, but we only see 2 right now. And oxygen's not balanced. We got 2 oxygens on the left side, but we have 1 here and 2 more there. There's a total of 3 oxygens on the right. So both hydrogen and oxygen are not balanced. Okay, let's not change the subscripts. Don't change the recipe, but instead save the simplest molecule for last. So which of these 4 molecules is the most simplest looking? Oxygen. This molecule only has a single element, oxygen. There's 2 elements in methane. There's carbon and hydrogen. Water has 2 elements, hydrogen and oxygen. Carbon dioxide, 2 elements. 2 different atoms, 2 different types of atoms, carbon and oxygen. Okay, so save oxygen for last, which means put a big number in front of this in the last thing that you do. And don't start balancing the oxygens. Save that for last as well. Okay, so that means start by balancing either carbon or hydrogen. You can start with either one. They both work. I'm going to start with the carbon, and we already saw that it's balanced. So carbon's done. There's 1 carbon on each side. But hydrogen's not balanced. We start with 4, and we only end up with 2. Well, that's not right. We probably have a second water molecule, so that together we have 4 H's on both sides of the equation. Okay, so now hydrogen and carbon are both balanced. We're at the last molecule, oxygen. Let's balance the oxygen molecules, and we want to just put a number in front of the O2. So we start with 2 O's, 2 oxygen atoms on the left side, and now on the right side there's 1, 2, plus 2 more is 4. So we're going to need another oxygen molecule, and together there's 2 oxygen molecules to give us 4 atoms of oxygen. So the balanced equation is 1 methane molecule reacts with 2 oxygen molecules to produce 2 water molecules and 1 carbon dioxide molecule. Last example. This one looks more complicated. Yeah, we got these crazy equations with parentheses. What this says is that there's 2 groups of PO4. So if you want to count up the total number of oxygens here, it's 2 times 4. Or in other words, this molecule has 3 calciums and 2 of these PO4 groups. That's what the parentheses with the little subscript 2 means. So these are all the atoms in this one molecule that exists as a solid. Okay, is this equation balanced? No, there's plenty of calciums on the right side, but only 1 on the left. The bromines, there's 2 on this side, 1 on that side. Phosphorus, the P, there's 2, and there's only 1. Yeah, it looks like everything's unbalanced. Great. All right, what's our hint? Let's start by identifying the simplest molecule and save it for last. Well, it's certainly not this crazy molecule. No, the simplest one is the one which has only 2 elements, lithium and bromine, and no subscripts. So that means save balancing lithium and bromine for last. Go after calcium or phosphorus or oxygen. I'm going to pick the calcium. Okay, there's 3 calciums on the right and only 1 right now on the left. So let's put a big number 3 in front of this molecule so that we have 3 calciums. But notice we're also going to have 6 bromines. 3 times 2 is 6. But we're not going to balance bromine yet. We're saving it for last. So calcium's balanced. Then maybe we'll go after phosphorus, the P. Well, on the right side there's 2 phosphorus. And on the left side there's only 1. So we need to put a big 2 in front of this so that we get 2 phosphorus. Okay, calcium and phosphorus are now balanced. Now let's go after the oxygen. Let's see, on the right side we have 2 times 4. There's 8 oxygens right now on the right. And there's 2 times 4, also 8 oxygens on the left. Good. 3 of the elements are now balanced, leaving lithium and bromine, saving the simplest for last. Let's go after those. You pick. Turns out they both work. If you go after lithium first, well, there's 1 lithium atom on the right, but there's 2 times 3, 6 of them. 6 lithiums over here on the left side. So we need to put a big 6 here to get 6 lithiums on the right side. And then looking at the bromines, well, there's 3 times 2. There's 6 bromines. And there's 6 bromines on the right as well. Hey, it's balanced now. Just add the physical states. This is aqueous dissolved in water. This one's also aqueous dissolved in water. This is a solid. And this one is aqueous. That's all for now. I'll see you in class.